be presenting on TracerX dynamic symbolic execution with interpolation. This has been a joint work which we have been doing during the time at National University of Singapore, and more recently we have joined other teams, but we are still working on the development of TracerX as an open source symbolic execution tool. So let me start with introducing the approach that we are using for the symbolic execution in TracerX. TracerX is built on top of KLEE, and we use KLEE as the symbolic virtual machine. On top of that, we perform interpolation to prune the subtrees inside the symbolic execution tree. And by interpolation, I mean that we gather information from already traversed symbolic execution subtrees, and we try them to prune the other subtrees. TracerX got the second place in the RERS 2020 challenge. From a C, we were using both tools, and it got the sixth place in TestCom 2020 and 2021. And this is our website and GitHub repository address. So let me explain how we differ from KLEE in a little bit more detail. We perform DFS forward symbolic execution to find feasible paths similar to KLEE. Unlike KLEE, we keep the intermediate execution states, and when a path is finished, we generate a path interpolation for the path. And then when all the paths below a subtree are traversed, we create a tree interpolation from the paths in the subtree as the conjunction of the path interpolants. And later we use the tree interpolants for subsumption of similar program points inside the symbolic execution tree. So for example, consider this example on the top left, where we are trying to prove that X is less than or equal to 24. And you can see the symbolic execution tree on the right-hand side. Now, inside this tree, program point 8A and 8B are similar, and program point 5A and 5B are similar. Now, what we try to do is that when the traversal reaches 8A and traverses the subtree below it, we will try to create a tree interpolant. And later on, when the traversal reaches 8B, we would try to check if the context at 8B implies the interpolant generated at 8A. And if that holds, then we prune the subtree below 8B. And similarly, we can do the same thing for 5B with 5A. And this way we would be able to prune a large portion of the symbolic execution tree. Now, let me try to explain how we generate an interpolant. The ideal interpolant would be weakest precondition. We can use a path-based weakest precondition for the path interpolant, and the tree interpolant can be simply the conjunction of the path interpolants. However, the issue is that WP is intractable to compute in general. As an example, in the previous slide, the program, if we have a combination of the three if statements, the first one being true, second one being false, and the third one being false, the weakest precondition would be this formula over here, which is quite difficult to maintain and use. Essentially, WP is exponentially disjunctive, as we know, and the challenge that we are facing would be to obtain a conjunctive approximation of the WP. Now, a path in TracerX, we try to compute an approximation of the weakest precondition, which still is a conjunction. We see a path as a sequence of assignment and assume instructions. The interpolant of an assignment instruction is pretty straightforward. We have a post condition, we have an instruction, and we try to compute the inverse transition of the instruction over the post condition omega. We have implemented this at the LLVM IR level for the different classes of the LLVM instructions, but I don't have time to go into the detail. I would just give an example. Assuming that the post condition is x less than or equal to 15, and the instruction is this one, then the weakest precondition that we compute would be z less than or equal to 13. Now, while the assignment instruction has only implementation challenges, the assume instruction is more complex. We have a context, we have assume B, and we have a post condition omega. The WP approximation is to find a C bar which generalizes the context C, and we can replace it by C, and still in combination of the assume instruction, it preserves the post condition omega. This is the general abduction problem. There is no general way of solving this problem, and we have to come up with a, let's say, customized algorithm to deal with this issue for the assume instructions. The algorithm that I will be presenting for the assume instruction is the heart of TracerX and what we have been trying to develop and use. And this kind of differs us from the other symbolic execution tools. So in general, going back to the context, assume instruction, and the post condition omega that we had, we compute the finest partitioning over the context C from C1 to Cn, such that the variables inside each of the CIs are disjoint. Similarly, we perform the same thing on omega 1 to omega m, where the variables are disjoint. Now, we can group the CI, the different CIs, into three different groups. The first group are the target independent CIs, which are not required for ensuring that the post condition hold. We simply replace them with true. In other words, we remove them. The second group are guard independent CIs, which we show them with CGI, and we compute them in this format. We ensure they do not share any variables with the constraints inside B, which is the assume. We simply replace the second group of CGI by omega GI. The guard independent part of the post condition is kind of taken and put in the place of the guard independent part of the context. Now we are left with the remainder of the CI. We cannot capture the exact WP for this group. As an example, assume over here that the context is Z equal to 5. On the other hand, we have the assume, which is X greater than Z minus 2, and we have the post condition X greater than 0. In this example, the weakest precondition would be Z greater than 2, and it is very difficult to capture this systematically. For this group, we do not make any changes to the CIs, we just keep the CIs. So in the end, the interpolation that we are generating for the assume instruction is a combination of the omega and the CI, omega ij's and the CIs. Now, before I continue, I would like to mention that our algorithm is fundamentally different from the CDCL used in SMT solvers. Over here, as I mentioned just now, we are making the interpolation that we are making is partly coming from the context and partly coming from the post condition. And we do not use any solver calls in our algorithm. In addition to that, we have some optional algorithms where the user can turn on or turn off for the remainder of the CI that are in the third group, and we are keeping them. So as an example, there are situations that we can eliminate a certain CI. For example, in this example over here, the CI in the context is not required to ensure that the post condition holds. As a result, we can just eliminate it, or we can do projection. The example that I just showed you in the previous slide can be solved using projection, and from, let's say, X greater than a combination of X greater than 0 and the assume instruction projected over the variable Z, we are able to get the WP. However, these optional algorithms might be expensive, so we do not, let's say, keep them by default. We are still in the process of developing these algorithms, and we are, let's say, the plan is to allow the user to turn them on or off. Now, let me quickly go to the experiment settings that we have. We have been experimenting on 47 programs from SBComp and the RERS challenge, which are the results can be accessed in this paper on the archive. We performed two sets of experiments. The first set is on all the targets in these 47 programs, which is 5,058. And we pick a certain group, which is hard targets, and they are 1,470. The criteria for a hard target is that KLEE cannot find it in 5 minutes. From us, it cannot prove it. And for the first group, we give 300 seconds. And for the second group, we give 600 seconds for each of the tools that we have compared with. We compared with KLEE, CVMC, and TracerX. The green color shows the reachable targets, the blue color shows the unreachable targets, and the red shows the timeout. And we define winning as a tool being fastest in proving a target, and we define, let's say, losing the other way around. TracerX in the first group, sorry, and TracerX in the first group of all targets was able to win over in 26% of the targets, and it loses in 2% of the targets. In the rest of the, let's say, targets, we can have ties. And but when we go to the hard targets, TracerX is able to win 54% of the targets, and it only loses in less than 5% of the targets. And as you can compare over here, the amount of timeout in the hard targets is much less in TracerX comparing to CVMC and KLEE. And in total, we are able to get much faster, we are much faster improving the hard targets. Now, as future directions, we are working on 3 different aspects, which we are hoping in 3 different application areas that we are hoping to use TracerX. The first application area is testing. We have a recent paper on MCDC coverage, which is published in ISTA 2021. I will refer to you to that to have a look on it. We also are trying to use TracerX in the domain of incremental quantitative analysis, which is required for ensuring safety of non-functional features in embedded systems and safety critical systems. In addition to that, we hope to be able to use TracerX in the combinatorial optimization, where we are trying to simulate a combinatorial optimization problem using a C program and then run TracerX to find an optimal solution for the initial problem. And the results have been submitted to CP 2021. In the end, as a conclusion, I would like to also share these few different papers and websites for further readings on TracerX. Thank you very much.